quantitative analysis of elements. In the last lecture, we have done qualitative analysis. Now, quantitative analysis means to calculate the amount or percentage of the elements present in the organic compound. So, first of all, let us do the estimation of carbon and hydrogen. Now, to estimate carbon and hydrogen, we heat the organic compound with cupric oxide. Now, carbon present in the organic compound convert into carbon dioxide and copper left in the test tube, and hydrogen if present in the organic compound, that will give H2O. So what we do, we have a tube. Here we supply pure oxygen and we have sample, means organic compound, and then there is a furnace. Which contain cupric oxide. And then it is attached to a U tube which is filled with calcium chloride, and next tube is it contains potassium hydroxide. One is calcium chloride tube and other is potassium hydroxide tube. Now this calcium chloride, it will absorb the moisture. So we weight this tube before the reaction and after the reaction. So difference in weight gives us the weight of water. And potassium hydroxide, it is a good absorber of carbon dioxide. So carbon dioxide is absorbed here and free oxygen, means excess oxygen, will go out. Oxygen, because if oxygen is in excess, then this combustion is complete. Obviously cupric oxide will give oxygen, but excess of oxygen in furnace, that convert, if there is leftover any carbon or hydrogen, so that will be converted into complete combustion of carbon and hydrogen takes place. There is no chance of formation of CO, etc. Right? So in this way, excess oxygen goes out and we get the mass of water and mass of carbon dioxide. Now, yes, difference in mass before the reaction and after the reaction of CaCl2 tube will give the mass of water, and the KOH tube, difference in weight before and after the reaction, that will give the weight of carbon dioxide. So let us say mass of CO2, that is x gram, and mass of H2O, that comes out to be y gram. Now you know that if we have 44 gram of carbon dioxide, molecular mass of carbon dioxide is 44. So in 44 gram, what is the contribution of carbon? 12. So that means mass of carbon in 44 gram of CO2 is equal to 12 gram. So mass of carbon in x gram of CO2, yes, 12 by 44 into x. Let us make it general. Take it. So in this way, percentage of carbon in organic compound, that is equal to mass of carbon divided by mass of organic compound into 100. So now mass of carbon is 12 by 44 into mass of carbon dioxide divided by mass of organic compound into 100. So in this way we can calculate the percentage of carbon in the organic compound. Now hydrogen, so you know hydrogen is estimated in the form of H2O. So again, mass of hydrogen in 18 gram of H2O, molecular mass of H2O is 18. So it is 2 gram. So mass of hydrogen in y gram of H2O, that's 2 by 18 into y. So percentage of hydrogen is again same, mass of hydrogen divided by mass of organic compound into 100. So it is 2 by 18 into mass of H2O divided by mass of organic compound into 100. So in this way we can calculate percentage of hydrogen, right? Okay. Now we can modify this method depending upon along with carbon and hydrogen which elements are present. So if organic compound containing nitrogen, if nitrogen is also present, so you know when this cupric oxide is used, nitrogen present in the compound, that is converted into nitric oxide or nitrogen dioxide, and if nitrogen is also converted into NO and NO2 along with carbon which is converted into CO2, so they are also absorbed in KOH along with CO2. That means we have to eliminate NO and NO2, means that should not go to the KOH tube. Okay, so in this case what we do, we modify this tube. here we place copper gauze or copper grid. So that copper gauze, what is the use of this copper grid? It will convert nitrogen oxide nitric oxide into back to N2. So it forms nitrogen gas, and at the same time NO2 if present, that is converted into N2. So in this way we can estimate the percentage of carbon if even nitrogen is present in the organic compound, but we have to modify the tube.
So what modification did we make? Oh, we were already using Cu and we already had O.
No, we are using CuO.
Yes,
CuO will convert carbon into carbon dioxide, hydrogen into H2O, and and nitrogen into NO and NO2. So at the end of the tube we will use copper gauze. So that will convert back NO and NO2 to N2. Okay. So N2 is not soluble in KOH, that will go out along with oxygen, and therefore we can have only carbon dioxide in KOH. Okay. Second modification, if along with substance containing halogen, so if halogen are present, cupric halide is formed in CuO, cupric halide is formed, and at the same time halogens are also formed. So this cupric halide and halogen, they are also absorbed by KOH. So now in this case what we do, we use silver gauze. So silver gauze will form silver halide, which are non-volatile, they are precipitates. So in this way, on modification of the tube, means at the end of the tube, in case of nitrogen we are using copper gauze, in this case we use silver gauze. Third modification, if sulfur is present, substance containing sulfur or sulfur and halogen both, then we use lead chromate. At the end of the tube we will place lead chromate, because lead chromate, when we heat it, it will give PbO, Cr2O3 and O2. Okay, so it will give O2. So here if we are not using even cupric oxide, it will serve the purpose, because it will give oxygen, that will convert carbon into carbon dioxide and hydrogen into water. At the same time sulfur is converted into sulfur dioxide. So sulfur dioxide is also soluble in KOH, but lead chromate react with sulfur dioxide, or even it will react with halogen, and it will give lead sulfate, it will give lead halide along with Cr2O3 and O2. So 4 even if phosphorus is present, phosphorus is converted into P2O5.
Yes.
So even lead chromate is useful for phosphorus as well. If phosphorus is present, it will give lead phosphate, okay. So these are the modifications we can do in this method, and this method is called Liebig's method. This carbon and hydrogen, this method is called now for nitrogen. Estimation of nitrogen. So estimation of nitrogen is done by two methods. First is Dumas method, and other one is Kaldal method.
All right.
Dumas method and Kaldal method. Now, in case of Dumas method, again we heat the mixture with cupric oxide. Different form of cupric oxide are used, like we use cupric oxide gauze, coarse cupric oxide, even reduced copper gauze, all of them are used. So carbon is converted into carbon dioxide, hydrogen into H2O, that we have already done, and nitrogen present in the organic compound in the presence of cupric oxide on heating, and then again there is a reduced copper there. So at the end we will get nitrogen gas and a small amount of oxides of nitrogen. But reduced copper, what is the use of this copper? Already we have done.
Yes, sir.
Oxides of nitrogen, when comes in contact with reduced copper, we get again nitrogen gas.
Yes.
So again there is a cylinder of KOH. Now KOH is a good absorber of carbon dioxide.
Yes.
So carbon dioxide and even water vapors, they are dissolved in KOH, but nitrogen gas, as that nitrogen gas is formed, let us say this is this tube, there are various type of cupric oxides, okay, and at the end there is a copper. For the safe conversion of any nitrogen into N2 gas.
Yes.
So ultimately what will happen, there is a cylinder containing nitrogen. Here there is a KOH. So what happened when nitrogen gas is formed? Nitrogen gas is collected above the cylinder because nitrogen gas is insoluble in KOH.
Yes, sir.
So KOH, there is a downward movement of KOH as pressure of nitrogen above KOH increases. So the pressure above it, that will give the volume of nitrogen. The downward movement of KOH will give us an idea how much nitrogen gas is formed. Means ultimately we will measure the volume of nitrogen gas at a particular temperature and a particular pressure. So we will get volume of nitrogen gas at a particular temperature and a pressure, right?
Yes.
So after getting the volume of the nitrogen gas at a particular temperature and pressure, we will apply ideal gas equation P1 V1 upon T1 equal to P2 V2 over T2. So we will calculate the volume of nitrogen gas at STP. We will calculate volume of the nitrogen gas at STP, and pressure of nitrogen gas it is equal to P minus aqueous tension. What is aqueous tension? It is
Applied by KOH.
vapor pressure of water vapors at that particular temperature. So this aqueous tension should be subtracted from total pressure, because when you have a gas above aqueous KOH, so nitrogen, there is a pressure due to nitrogen gas as well as due to water vapors.
Yes.
And you can calculate aqueous tension at a particular temperature that is fixed. We can take it from the literature. Even we Google it, what is the vapor pressure of water at this particular temperature. It is fixed. It is independent of volume. It is independent of the other things, total pressure. Okay, it depends on the temperature only. So that is fixed, and therefore we subtract it from the total pressure and then we put it here.
Yes.
So this is existing condition, and this is at a STP. So at STP, pressure is 1 atmosphere
Yes.
and temperature is 273.15, or we can say 273 Kelvin.
Yes.
And these are the existing conditions. Volume we have calculated from the downward movement of KOH, and in this way at the end we will get V2, which is the volume of nitrogen gas at STP. Let us say this is volume in ml. So now we know that mass of nitrogen present in 20 to 400 ml of nitrogen gas at STP is equal to, yes, what is the mass of nitrogen gas present in 22 400?
This will be 28 grams.
Yes, it is 28 gram, because you know this is the molar volume. Yes, 1 mole of nitrogen gas and is 28 gram. So mass of nitrogen is present in V2 ml of nitrogen gas at STP. So it is 28 by 22400 into V2 gram. So percentage of nitrogen in organic compound is equal to mass of nitrogen in organic compound divided by mass of organic compound into 100. So mass of nitrogen is 28 by 22400 into volume of nitrogen gas at STP divided by mass of organic compound into 100. So that is the percentage of nitrogen we can calculate by using Dumas method. Then come to Kelda's method. So Keldal method is again used for the estimation of nitrogen in the organic compound, but there are few compounds where we cannot apply it, like if nitrogen is present in ring, like pyridine,
Yes.
or quinoline, any compound in which nitrogen is present in the ring, we cannot apply it. Even we cannot apply it in azo compounds, compounds containing N double bond N.
Like orange tie, red tie.
Yes, or we cannot use it in case of nitro compounds.
Is Dumas method applicable for these conditions?
Yes, Dumas method is applicable for all. So now in this case, what we do, nitrogen present in the organic compound, first we treat it with concentrated H2SO4. So whole nitrogen present in the organic compound, that is converted into ammonium sulfate. So nitrogen from the organic compound, it is treated with excess of concentrated H2SO4. So whole nitrogen is converted into ammonium sulfate. So ammonium sulfate, then we react it with excess of sodium hydroxide. So whole of the ammonia, sorry, whole of the ammonium nitrogen which is in the form of ammonium sulfate, will give us ammonia gas. And this ammonia gas, there it is salt, water, ammonia is a base.
Yes.
Now this ammonia is collected and it is titrated with standard solution of H2SO4. What do you mean by standard solution?
100% concentration.
No, whose molarity is known to us, whose concentration is known.
Okay.
That is called standard solution. Okay. Anywhere if we are writing standard solution of this particular compound, standard solution of HCl, standard solution of NaOH, means its molarity is known. So again, now here H2SO4 is used whose molarity is known to us, and we use excess of H2SO4 so that whole of the ammonia which is evolved in this reaction is again converted into ammonium sulfate. So now you see H2SO4 is used in excess.
Yes.
So let us say this excess of nitrogen, we use VmL of H2SO4 of molarity M. So excess of H2SO4 means which is left over after reacting with ammonia, that is titrated against NaOH. So and it has again same, NaOH has same molarity. So again it gives sodium sulfate and H2O.
Yes.
So let us say mass of the organic compound is m gram and volume of H2SO4 taken, where H2SO4 taken, this one.
The excess.
Yes, let us say it is VmL of molarity capital M. Now the leftover H2SO4, unused H2SO4, to neutralize it we use NaOH. So
Yes.
volume of NaOH used for titration of excess of H2SO4. So let us say it is small VmL of same molarity. Now, if NaOH and H2SO4 are used, we use normality equation,
Yes.
N1V1 equal to N2V2, and molarity of NaOH is M, volume of NaOH used is V, normality its N factor is 2,
Yes.
so 2 into M into V.
Yes.
So M cancel, means volume volume of H2SO4, that is V by 2. Whatever volume of NaOH is used, half of volume of H2SO4 is used up.
Yes.
So in this way, actual volume of H2SO4 used to neutralize ammonia is equal to V minus V by 2 ml
Okay.
of molarity capital M. Okay.
Yes.
So if H2SO4 volume of H2SO4 used is to neutralize ammonia is V minus V by 2 ml of molarity M. So if ammonia has same molarity, then what is the volume of ammonia? See, 1 mole of H2SO4 requires 2 moles of ammonia.
Yes.
That means double volume of ammonia is used up.
Yes.
So that means volume of H2SO4 used to neutralize ammonia is this. So volume of ammonia,
Would be 2 times of this.
yes, of molarity M, of same molarity, is equal to 2 times V minus V by 2. Okay.
Yes.
Now, if we have 1000 ml of 1 molar ammonia, solution, then what is the mass of ammonia?
17, sir.
17 gram, right?
Yes.
And what is the mass of nitrogen?
14.
Yes. So that means mass of nitrogen present in 1000 ml of 1 molar ammonia solution is equal to 14 gram. So now mass of nitrogen present in 2 into V minus V by 2 ml of capital M molar ammonia.
Yes.
So it is equal to 14 divided by 1000. See, 1000 ml 14 gram. So 2 into V minus V by 2 ml.
Yes.
So it is 14 upon 1000 into 2 into V minus V by 2. And here 1 molar divided by 1 into capital M, because now it is M molar.
Yes.
So this is the mass of the nitrogen. So what is the percentage of nitrogen? So percentage of nitrogen is comes out to be 14 divided by 1000 into 2 into V minus V by 2 into capital M into 100 divided by mass of organic compound.
Sir, why are we taking 1000
see, we have taken 1000 ml of 1 molar ammonia.
Yes.
So instead of 1000, we take 2 into V minus V by 2 ml, which is actual. So 1000 ml has 14 gram. So 1 ml has 14 upon 1000.
Okay, so we don't need to use 17.
There is no need to use, because we are concerned, we are actually finding the mass of nitrogen
Yes.
instead of ammonia. So no doubt ammonia has 17 gram, but we need to know the mass of nitrogen actually.
Okay.
So I'm directly using mass of nitrogen present in this particular 1000 ml and 1 molar ammonia.
Alright.
Okay. So in this way, 2 0 cancelled. So 1.4 into 2 into V minus V by 2 into capital M divided by mass of organic compound. So this is the percentage of nitrogen by Kjeldahl method.
Understood.
This 2 is used because basicity of acid is 2. 2 is actually basicity of the acid used.
Understood.
If there is a HCl instead of H2SO4, so we will use here 1.
Yes.
So we can, in general, we can write it as 1.4 into basicity of the acid
Okay.
into volume of the acid, total volume of the acid used, minus volume of NaOH used to neutralize the excess of acid divided by 2 into molarity of the acid used divided by mass of organic compound. Now sometime what happened, volume of NaOH is not given. If volume of sodium hydroxide is not given, okay, so if volume of sodium hydroxide is not given, just put it 0.
Okay.
So this is the formula to calculate percentage of nitrogen by Kjeldahl method. Now next is estimation of halogen. By Carius method. So in Carius method, chlorine is estimated in the form of AgCl. Bromine is estimated in the form of AgBr. Iodine is estimated in the form of AgI. So what is the atomic mass of chlorine? 35.5.
Yes.
And silver is 108
108. Yes.
plus 35.5, so it is 143.5 gram.
Yes.
Bromine it is 80. So silver is 188. Iodine is 127. So it comes out to be 235.
Yes.
So percentage of chlorine is equal to 35.5 divided by 143.5 into mass of AgCl divided by mass of organic compound into 100. That's it. And what about percentage of bromine?
Similar, sir, we just use
80 upon 188 into mass of AgBr,
upon mass of organic.
mass of organic compound into 100,
Yes.
and percentage of iodine. So it is 127 by 235 into mass of AgI divided by
mass of
organic compound into 100. On similar lines, sulfur is estimated in the form of barium sulfate. This method is also called Carius method. So sulfur, it is 32 gram.
Yes.
And barium is 137. 32 plus 16 4 is 64. So it is 233.
Yes.
So percentage of sulfur is 32 divided by 233 into mass of barium sulfate divided by mass of organic compound into 100.
Yes.
And last is phosphorus. So phosphorus is estimated in the form of ammonium phosphomolybdate.
Oh.
Already we have done in qualitative analysis.
Yes.
So keep in mind its molar mass, you have to remember it is 1877. So in ammonium phosphomolybdate there is only one phosphorus. So it is 31.
Yes.
So percentage of phosphorus is 31 by 1877 into mass of ammonium phosphomolybdate divided by mass of organic compound into 100.
Yes.
Or sometime it can be estimated in the form of magnesium pyrophosphate. This is Mg2P2O7. So in this case there are two phosphorus.
Yes.
So it is 62 gram and it is 2 into 24 plus 2 into 31 plus 7 into 16. So it comes out to be 222 gram.
Okay.
So percentage of phosphorus we can calculate by using, it is 62 by 222 into mass of magnesium pyrophosphate divided by mass of organic compound into 100. So in this way we can calculate the percentage of phosphorus. Now last is estimation of oxygen. So percentage of oxygen is equal to 100 minus percentage of all the other elements. Okay.
Yes, sir.
Or if you want to calculate it directly, then what we do, first we have compound, we heat it, so it give O2 along with other gaseous products. So to calculate percentage of oxygen directly, first what we do, we heat the mixture, and there are various gaseous products along with oxygen is formed. So then there is a red hot coke at 1373 Kelvin. At high temperature, when carbon is burned at high temperature, instead of carbon dioxide we get carbon monoxide.
Yes.
because carbon monoxide is thermodynamically more stable than carbon dioxide. So at 1373 Kelvin, whole of the oxygen present in the organic compound, that will give carbon monoxide, and then this mixture is heated with I2O5. So I2O5 will give I2 and 5 CO2. So overall reaction is multiplied by 5 and by 2. So overall we will get, it is 5 CO, right? So we will get I2, 2 I2O5, 5 to the 10 carbon, sorry 2 I2O5, CO cancelled, and 5 O2, so 2 I2 and 10 CO2. So overall, 5 O2 is equivalent to 10 CO2, and it is equivalent to 2 I2, or we can say one oxygen, if there is only one oxygen. You see, there are 10 oxygens actually. 5 O2 means 10 oxygen. So one oxygen is equivalent to 1 CO2 and is equivalent to 1 by 5 I2. 2 by 10 I2 means 1 by 5 I2. So either if we know the mass of iodine liberated or mass of CO2 formed, we can calculate the percentage of oxygen. So percentage of oxygen in terms of carbon dioxide. See, one oxygen is equivalent to 1 CO2.
Yes.
And what is the mass of one oxygen? That is 16. 16 divided by 44 into mass of CO2 divided by mass of organic compound into 100. Got it?
Yes.
And in terms of iodine, percentage of oxygen in terms of iodine. So 2 I2 is equivalent to 5 O2.
Yes, sir.
Means 10 oxygen is equivalent to 2 I2, or we can say 5 oxygen is equivalent to 1 I2. That means 5 into 16, that is contribution of oxygen, divided by 2 into 127 into mass of I2 formed divided by mass of organic compound into 100. Okay. So this is all about the percentage of all the elements present in the organic compound. Nowadays we use CHN elemental analyzer.
Okay, sir.
This is an instrument, just 1 to 3 milligram of organic compound is required and it will give percentage immediately. Means on the screen there is a percentage of carbon, hydrogen, nitrogen. Even CHNS is applicable in some universities. So CHNS analyzer is also available, where you can find out percentage of carbon, hydrogen, nitrogen and sulfur present in the given organic compound, right?
Yes.
Okay, so that's all about quantitative analysis of organic compounds.